Good morning. This is your stat sensei, Mr. Spensey, and we're going to do normal distribution and the distribution of means, so central limit theorem. So a brake manufacturer designed a new brake pad for long haul trucks. Repeated tests were conducted on long haul trucks transporting a load of 75,000 pounds at 70 miles per hour. The braking test showed that the new brake pad allowed the trucks to stop completely in an average distance of 515 feet. So, okay, the word average is important because that's telling us this is our mean. So our mean distance is 15 feet, 515 feet with a standard deviation of 62.5. The braking distances are normally distributed. All right, so that tells us we can use the normal regardless of the sample size, regardless of what we're doing. So we're going to be working with the normal. What is the likelihood that a single long haul truck with a new brake pad has a braking distance between 545 and 605 feet? Well, the word single tells me I'm working with one truck, so my sample size is one. So this lets me know that I'm going to be working with a normal CDF. So I know already that this is going to be a normal CDF problem. Okay, because it's normal and I'm working with one. So if I'm drawing my picture of this and it's normal, we have a mean of 515. In this case, they want to know what's the probability that it's 545, which is above it, to 605. So now we have a lower bound and an upper bound. So let's go ahead and write our calculator commands, which are norm CDF. The lower bound is 545. The upper bound is 605. Our mean is 515, and our standard deviation is 62.5. So lower, upper, mean, standard deviation. Let's go to our calculator. Second vars, norm CDF, which is our second one here. And our lower bound, the lowest part of our shading was at 545. The highest part of our shading was at 605. Our mean was 515. And our standard deviation was the 62.5. And we see, oh, it's about 24%. So 0.2406 is our response to this question. The next one, what's the probability that a randomly selected sample of 15, hey, that's important, our sample size is 15, will have a mean, so they're asking about my average or this, so now we're talking about the sampling distribution of the means. We're talking, and so we'll be using central limit theorem. Our graph is going to look very much similar, all right? So let's draw our picture. We're still going to be working with a normal curve. Now, some of you may be going, hey, but your sample size is only 15, and normally you'd have to be 30 or more. Well, that applies if it's not normal. But they told us the underlying distribution is normal, so we're good to go. So our mean is still 515. And the population standard deviation they told us before is 62.5. Notice I said the population standard deviation. That's not the standard deviation of X bar. So, because the standard deviation of X bar would be 62.5 divided by the square root of 15. So if they had asked for that, you would have gone 62.5 divided by the square root of 15. But they didn't ask for that, so we don't have to worry about that here. So normal, because we're working with the X bars, we probably want to use the z-test function of the calculator. It's a little bit easier. And under z-test, the very first thing it's going to ask for us is our mean. Then it's going to ask for the standard deviation of the population, which happens to be 62.5. Then it's going to ask us for the X bar. Well, they said a stopping distance of at least 545. So that means 545 or more. So my X bar is 545. My next thing it'll ask for is my sample size, which is be 15. And then they're going to ask for which way do we want to shade, and we shaded up and to the right, so we're going to shade a greater than. So second vars, stat, test, z-test. My lower bound is 545. My standard deviation is 62.5. My X bar, my mean is 515. My X bar is 545. And my sample size is 15. Make sure we have it shaded up and to the right. We press calculate. And I end up getting a p-value of 0.0315. I also got a z-score, but the p-value is what I need right now. All right, so that's the probability. That's how much area. So there's about a 3% chance that a group of 15 trucks would have a stopping distance, an average stopping distance greater than 545. The distribution of SAT scores is approximately normal. Oh, that's important, because that means I'm going to be working with a normal with a mean of 1,051. And a standard deviation of 211. For the purposes of exam, assume that the students at Somerset High School have the same mean and standard deviation as the population. What is the likelihood that a randomly selected Somerset student who has taken the SAT has earned a score between 1,070? So A random, A means 1. So my sample size is 1. So that tells me I'm going to be working with the norm CDF. I'm not going to be working with the distribution of means here because we're working with a single person. So when I look at this, my mean is 1,051. And they want it to be between 1,070 and 1,240. Well, 1,070 is definitely above 1051. And 1,240 is also above it. So we're looking for this area shaded right there. So this is a norm CDF because it's normal and we're working with a sample size 1. My lower bound is 1,070. My upper bound is 1,240. My mean is 1,051. And my standard deviation is 211. So lower, upper, mean, standard deviation. Second vars, normal CDF, 1,070, 1,240, mean of 1,051, and a standard deviation of 211. And I end up getting 0.2789. So the probability a single student would be in that range is about 28%. All right. What is the probability that the average SAT score of a random sample of 25 students is less than 1,000? We're talking about average, so that's distribution of the means or distribution of the X bars. And we have a sample size 25. So this is going to be a z-test. We'll want to use a z-test function. You can use the normal CDF, but a z-test function will be easier. Our drawing is going to still be similar. We're still going to have our mean set at 1,051. And our X bar is at 1,000. And they said is less. That means I'm shading to the left. So z-test. And the first thing it's going to ask me for is my mean, which is 1,051. Then it's going to ask me for my standard deviation, which is 211. Then it's going to ask me for my X bar, which is 1,000. And then it's going to ask me for the sample size, which is 25. And then our shading, in this case, we're shading to the left. So stat, test, z-test. 1,051, 211, 1,000. Oops, for the X bar is 1,000. My sample size is 25. And we're shading to the left. Make sure we select that and press enter. Calculate. And we get 0.1134. So my shaded area or the shaded probability is about 11%, 0.1134. All right, that takes care of that one. So let's look at the next one. The manager of a cultured pearl farm has received a special order for 2 pearls between 9.5 millimeters and 10.5 millimeters. So my size is between 9.5 to 10.5. So if I have a pearl that's size 10, it's a good size. 9.6, good size. If it's 10.6, it's too big. If it's 9.4, it's too small. So less than 9.5, too small. Greater than 10.5, too big. But in between, it's just right. From past experience, the manager knows that the pearls in his oyster farms have diameters that are normally distributed. Hey, that means we're working about the normal. We don't really have to worry much about sample size. With a mean of 8.5 and a standard deviation of 3. Assume every oyster contains 1 pearl. What's the probability a single pearl is too small to satisfy? That means the pearl has to be less than 9.5. So let's draw a picture of this. Now this picture is a little bit confusing, I have to admit, because sure, our mean is 8.5. Well, 9.5 is above it, but anything less than 9.5, so anything in this area is too small. All right, because it's a single pearl, that means that my sample size is 1, and with a sample size of 1, we're using a norm CDF. My lower bound, well, I shaded all the way to negative infinity, and then I shaded all the way up to 9.5. So negative infinity is my lower, this is my upper. My mean is 8.5, and my standard deviation is 3. So this is my mean, this is my standard deviation. So let's get that in there. So second vars, normal CDF, oops, negative 9 raised to the 99th power. The upper is 9.5, but the mean is 8.5, and the standard deviation is 3. And I end up with 63%. Well, that sort of makes sense because we're over halfway. This would be 50%, we're over halfway, so 63% probably is a good answer. So 0.6305. What's the probability the average diameter of 5 pearls is greater than 9 millimeters? So let's use the word average, which is means or X bar. So this is distribution of the means, and sure enough, we have a sample size of 5. So N is 5. However, our mean is still 8.5, and our standard deviation is still 3. Now, I'm not asking about the standard deviation of X bar there. I'm just asking about the standard deviation. Okay, so we're going to draw our picture. So 8.5 is our mean. And then we want greater than 9. So 9 and shading up to positive infinity. That's what we're looking for. Well, we have a sample size 5, and we're talking about averages or mean. So this would be best to use the z-test function of the calculator, which will first thing it'll ask for is the mean, which is 8.5. Then it'll ask for the standard deviation, which happens to be 3. Then it'll ask for the X bar, which is 9. So this is my X bar, this is my mean. And then it'll ask for the way to shade. Well, we're shading up, so this is a greater than. So with that said, second vars, stat test, z-test, and we have a mean of 8.5 We have a standard deviation of 3. We have an X bar of 9. Oops. So I can quit. Stat test. Got to be careful with these fat fingers of mine. I left off the sample size. My sample size is 5, and then we shade up. Important to have that sample size. So the sample size of 5, and make sure that we're shading up and press enter after that, drop down and hit calculate. And we end up with 0.3546. So our P is 0.3546. All right, the next one. What's the likelihood that a randomly selected pearl meets these size requirements? Well, what was the size requirements? Oh, it had to be 9.5 to 10.5 millimeters. So our size requirement is 9.5 to 10.5. That's our size requirement. But it's a randomly selected pearl, so that tells me N is 1. We're still dealing with a mean of 8.5 and a standard deviation of 3. But because our sample size is 1, and we're not talking about averages, we're going to have to use a norm CDF. All right, so drawing our picture, 8.5, and then we need to be 9.5, which is above it, up to 10.5. So anywhere in that area is a good size pearl. Well, because our sample size is 1, we're going to use the norm CDF. It's usually better. And it'll ask us for the lower bound, which is 9.5. It'll ask us for the upper bound, which is 10.5. Then it'll ask us for the mean, which is 8.5. And then it'll ask for the standard deviation of 3. Lower, upper, mean, standard deviation. Please note that's 9.5, 10.5, 8.5, and 3, because that does not look very good. 8.5 and 3. Hopefully that helps. All right. So second vars, normal, CDF. Lower bound, 9.5, because that's the lowest part of our shading. Upper bound, 10.5, because that's the highest part of our shading. Our mean is 8.5, and our standard deviation is 3. And we find out that there's about 11% chance that that would happen. So 0.1169 is our response to that. All right. Beef ranchers sell cattle at auction. The more cattle weigh, the more the rancher makes. While there are numerous factors that determine the weight of cattle, the rancher can impact the size of the cattle by waiting until the calves are older and by changing the quantity and quality and type of food the calf receives. One particular rancher has a herd of cattle in which the weights of its calves are normally distributed. That's important because then we don't have to worry about the sample size being 30 or more, with a mean of 560 and a standard deviation of 123. So what is the likelihood that a randomly selected calf, so in this case A, that tells me it's one single calf. Because it's a single calf, this is going to be a normal CDF, weighs between 480 and 525 pounds. So let's draw a picture of this. The mean is at 560. 480 and 525. 480 is below, and so is 525. So 525 is below, and so is 480. So both of them are below. So that's what we're looking for. And because it's a single cow, it's a single value, and because it's normal, we're going to use the norm CDF with a lower bound of 480 and an upper bound of 525, a mean of 560, and a standard deviation of 123. Second vars. Normal CDF. Lower bound 480, upper bound 525, mean is 560, and a standard deviation of 123. And we end up getting 0.1302. So there's about a 13% chance of having a calf of that size, which happens to be smaller than the average calf. 18 of these calves that are ready for auction were randomly selected. Okay, so they were randomly selected, and we have a sample size of 18. What is the likelihood that their mean weight, so the X bar or the average? Well, this tells me I'm going to be working with the Z-test because I have more than one. I'm going to go ahead and make that note to myself so I don't forget. And I'm going to draw my picture. And the mean is still 560. We want to know what's the likelihood that it weighs 600 or more. So this is my mean, and that's my X bar. So the very first thing the calculator under Z-test will ask for is the mean, 560. Then it'll ask for the standard deviation. Well, our standard deviation, we said before, was 123. 1, 2, 3, A, B, C. Go Michael Jackson. The X bar is the next thing it asks for, which is 600. The sample size was 18, and then we're shading up and to the right, so it's a greater than. So second vars, excuse me, stat test. So I want to get to the Z-test. My mean was 560. My standard deviation is 1, 2, 3. My X bar is 600. And my sample size was 18, and we're shading, oops. And we're shading up. So I have everything in there. And I come up with about an 8% chance, 0.0838. All right. So if we're working with one, it's probably going to be a normal CDF. If we're working with more than one and it's normal, then we're going to be working with the Z-test most likely. All right. Appreciate you watching. Hope to see you on the next one.